Hi, I'm Ben-Yaakov. This presentation is concerned with DC errors in operational amplifiers. Okay, let's start with the problem related to the offset voltage. To understand the problem, let's do a mental experiment. Suppose you have an amplifier, has some supply to it, and we short the input. Let's put it to ground too. Now, one would think that in this case, the output voltage will be zero. Well, wrong. In most cases, one will find that the output voltage is non-zero, and many times it'll be actually very high levels, very close to saturation, either to the V plus voltage or to the negative rail, V minus. In order to correct this, one can put a small adjustable voltage source, and it will be possible to adjust this voltage source until the output is indeed zero. Now, this voltage required to adjust the output to zero is called the offset voltage. Now, this experiment that I'm showing here is really a mental experiment. This is not the way we're going to measure the offset voltage because this adjustment is going to be extremely sensitive. We are talking about very small voltages, like in the millivolt ranges. The first thing to do is to model this offset voltage. The way we do it is we assume that we have, like in the core, we have an ideal amplifier, and then we put the offset voltage in series. Well, 2 points to consider. Number one, since this offset voltage is due to some random error in the production, the polarity is unknown. So it really doesn't matter. We are always talking about the absolute value of this voltage. A second point to consider is that since this is here an ideal amplifier is a differential amplifier. It is sensitive to the voltage between its input terminals. So one can actually put the offset voltage the way it is shown here, or put it here. Doesn't matter. This is the same model. Now, this model now explains why is it that when we put the offset voltage at the input, I will get zero, because if you put here a source which is just canceling out in this loop here the internal, so to speak, offset voltage, the output will be zero. So we have now a model that we can use in order to evaluate what are the errors at the output due to this offset voltage. First thing to consider would be a non-inverting amplifier. This is a configuration of the non-inverting amplifier. And again, we are going to put the offset error, the source which represents the offset error, in series with one of the inputs. Again, we could have put it here, but as you'll see in a minute, it's really much nicer to put it here, because then you can get the result immediately. Okay, now in order to evaluate the effect of a V offset on the output, we can use superposition. In this case, we're going to represent the input by a short. And in this case, we see that the offset voltage is like an input to the amplifier. Consequently, the normal gain of this amplifier, which is R1 plus R2, these are two resistors, divided by R2, applies also to V offset, and consequently, the V out will be V offset times this gain, which implies that the offset voltage is amplified practically the same way as the input voltage. Okay, Now, what happens with the non-inverting amplifier? Here we have a non-inverting amplifier. In this case, the gain is minus RF over Rin. Again, I'm going to put the V offset here, and we'll explain in a second why this is convenient. And in this case, then, we have to evaluate the effect of this offset voltage on the output. Now, although this is an inverting amplifier, when we use superposition, and in which case we are going to replace the input with a short, this amplifier is in fact a non-inverting amplifier with respect to the offset voltage. In other words, the difference between an inverting and a non-inverting amplifier is actually the question, where do you feed the input? Whether you feed it here or you feed it here. Once you eliminate the input voltages by superposition, the two amplifiers are the same. And here I'm representing this so-called inverting amplifier. For the case of the offset voltage, I've just redrawn it. This is the same circuit exactly. See, RF here and RF here, R in and R here, when this is, of course, shorted. So to show that these are the same circuits, and consequently, the gain with respect to V offset is the same. So in this case, it'll be like if I have it here, it'll be like RF plus Rin divided by Rin. Now notice that there is a slight difference between the gain with respect to V offset and the gain with respect to V in. With respect to the normal input to the inverting amplifier is minus RF over Rin. We are not concerned about the negative sign, but just the fact that this is RF plus Rin. However, you can write this equation, in fact, as RF over Rin plus 1. So the difference between two is this one. And if RF over Rin is large, that is, if you have high gain cases, then the one probably doesn't make a big difference. And again, you see that you amplify the V offset just about as you amplify the V in. Now this implies that if you have a source of, say, 10 millivolt, and your amplifier has an offset of, say, 5 millivolt, this is very bad, because you don't know whether the output that you develop is due to the offset voltage or to the input, because they are amplified the same way. Now, this holds for DC inputs only. Many a times, you'd like to amplify a source which is an AC source, say an audio source, a microphone signal. Well, in that case, you really don't need a DC amplification. And in this case, it is possible to separate between the AC amplification and the DC amplification. For example, in the case of the inverting amplifier, I could put in a series capacitor. Now, intuitively, one can understand that at high frequency, when the impedance of this capacitor, 1 over omega C in, is becoming much less than Rin, then obviously the gain is again RF over Rin, well, with the minus sign if you wish. However, the situation is entirely different for the offset voltage now. The reason is that for DC, this is like a open circuit, the capacitor, because the impedance is very high. Consequently, we have an amplifier like this, which is basically a follower. We at this stage neglect the current going into the amplifier, so the potential here is like the potential here. So this is basically a follower. So lo and behold, the gain for V offset in this amplifier is 1 because there is a 0 between these terminals. This is actually V out, which means that V out is equal to V offset. However, as already mentioned earlier, at high frequency, we can obtain any gain we wish by selecting RF over Rin to be the desired value. Okay, we now move to another source of error, which is due to the input current. Now, in an operational amplifier, which is built with BJT transistors, bipolar junction transistors, typically we'll have at the first stage a differential amplifier, and we are actually at the input looking at the bases here. Now, in this case, of course, there is some bias going into the base, so we are going to see some current going into the input terminals of the amplifier. Now, if this is a MOSFET, CMOS type amplifier, these currents are going to be very small. Still, there are going to be some current due to leakages and some other effects. So always there's some current. However, in MOSFET-based amplifiers, these currents are going to be very small. Now we can now enhance our model. After we've put in the V offset, we can put 2 current sources to represent the input current going into the amplifier. Okay, this is again, so the practical amplifier. This is ideal amplifier, meaning that there is no current going in here. So these sources draw the current coming from the input. The direction of these currents depend on the type of transistors that we have at the input. Like for a transistor of NPN, like shown here, indeed the current will be getting in. However, if these transistors are PNP transistors, the current will be coming out. Well, again, normally we are concerned with the absolute value, so the sign here, the polarity, will not be that important in our discussion. So now we can see what is the effect of these currents on the output and what will be the value or the DC error due to these currents. Again, we can use superposition. And in this case, since this is a voltage source, I'm representing it by a short, 0 voltage. And I see that IB plus in this case, actually it's going to ground. Well, there's no current here. And consequently, it's not important. So the only current which really makes a difference is this IB minus. Now, this is a bit confusing. The question is, what is the effect of this current on the output? Well, again, contrary to intuition, one would think that, say, Rin is affecting this value of the output voltage because this current is sort of splitting between the two. Well, wrong. As it turns out, the current through Rin, this current, is 0. Well, the reason is that between the input terminals of the operational amplifier, the voltage is just about 0. Consequently, on Rin, which is now connected here to ground, the voltage drop is 0. Having a voltage drop of 0, the current will be 0. This implies that all the current is coming this way. Since this is the potential of ground, this is the virtual ground point here. So the output voltage as a function of this input current can be now calculated as a function of our RF. Okay, now what happens with the non-inverting amplifier? Well, keep in mind again that for a case in which we, by superposition, eliminate the effect of the input, like here, there is really no difference between the non-inverting and the inverting amplifier. As you can see, this circuit is just about equal to the inverting amplifier, except that in the case of the inverting amplifier, the input was here, but again, in superposition, we shorted, so it really doesn't matter. And for the reasons already discussed, the current will not split here, but rather will go this way only. Or, put it another way, the voltage here is 0. Consequently, this is actually the voltage across R2. So the voltage across R2 is 0, and there is no current flowing through it. But let me pause for a second just to clarify the fact. Why is it that, or what makes this phenomena that there be no current here? Well, the idea is that if indeed there be even a little current here, it'll develop a voltage that will be fed to the amplifier. The amplifier will respond, and since this is negative feedback, the response will be opposing this effect until the voltage will be high enough so as to suppress the voltage across R2. So the feedback effect is a mechanism that is actually causing the voltage across R sub 2 to be 0. So we can now summarize the two cases, which are the same. In the case of the inverting amplifier, which is this one, the current is flowing through RF, and with the polarity shown here, actually the direction of the current is this direction, the positive direction. So therefore, the output will be IB minus times RF. In the case of the non-inverting amplifier, that's the same case, because once I eliminate this input voltage, then again we have a circuit which is basically the same as the inverting amplifier, except that it is drawn differently. And of course the current will be this way, and we'll get IB over R1. So to summarize, the error, the DC error due to the input current to an operation amplifier are primarily affected by this feedback resistor, RF or R2 in this case, and they're just the product of this current times R2. So if you use very large resistors, you may have large DC current, DC errors. Now the question is, can we do anything about it? Can we reduce the error at the output due to the input current? Well, as it turns out, we can do it. The way to do it is to add some resistance at a plus input terminal. Now, what this really is causing is actually it is causing an output voltage which is of opposite polarity as the one caused by the IB minus. Well, this stands for reason because this IB minus goes to the input and minus input. This IB plus goes to the plus. So the polarity of these effects will be sort of opposing each other. So if you're clever enough to choose this Rx, then you might be able to actually cancel out the effect of IB minus by IB plus and the selected Rx. So what should be the value of Rx? Well, there are a number of ways to do it. To do the calculation, I'll do it in a sort of a formal way. What you do is you use superposition again. First of all, we replace Vn by short because Vn has nothing to do with what we are talking about. Secondly, we look first of all at the effect of IB plus, assuming of course the IB minus is 0, and IB plus, which is now, let me turn this one off, going through Rx, developing a voltage IB times Rx minus due to the direction of the IB plus, and then amplified, because from here to here, this is a non-inverting amplifier. And then we look at the effect of IB minus when IB plus is 0. In this case, we know that the current is flowing this way, so this is the effect of IB minus. So now we want to cancel out one by the other, so we equate the two. And for the case that these IBs, that is the bias current of the input, the two input terminals are the same, we get this expression. This expression says that Rx should be equal to, in fact, Rf in parallel to Rn, because Rf times Rn divided by Rf plus Rn is actually Rf in parallel to Rn. Okay. So what is happening in the case of non-inverting amplifier? Well, again, it's the same case. Working with superposition, you have the same circuit, except that in this case, you have to put Rx here. I mean, it's the same way, except that it is not connected to ground, but rather in series with the input terminal. And the rules will be, of course, the same. Now, although we found a equation or a way to calculate Rx, I'm going to show you an intuitive way which could be very helpful in cases in which the calculation might be rather elaborate. What is the idea? Well, the idea is that we find what are the conditions that need to prevail at the input terminals of the amplifier if the amplifier itself would not be in and the output will be short-circuited. In other words, what I'm doing, I have just cut out the amplifier and connected the output or the node of the output to ground. Okay. Now here we have two current sources which now are seeing an impedance here and an impedance here, or resistances here and here. And of course, we can find out the value of Rx such that the potential here will be exactly the potential here. Now, if IB is the same, then IB times Rx, this is the potential at the positive point, should be, I'll explain why in a second, equal to the potential here, which is found by IB times Rf in parallel to Rn. I want to make these two potential equal such that when I'll put back the amplifier, and of course very quickly cut out the short, the amplifier will see 0 voltage in between the terminals. And if it will see 0 voltage, the output will be 0, and this is exactly the situation we are talking about. So the bottom line is that the Rx should be chosen such that when you look from the input, the positive or the plus input of the amplifier, you see a impedance or a resistance which is equal to the resistance seen from the negative input terminal. If these two resistances seen by the two sides are equal, then you have a correct compensation, and by this you can very quickly calculate Rx. Now comes the question, what if IB plus and IB minus are not equal? And indeed they are not. In a practical amplifier, you'll find that there is a difference between them, and the difference is called offset current, input current, offset input current. Now, to analyze this situation, after we already put in Rx under the assumption that the currents are equal, in order to analyze this situation, what we do, we represent one of them, let's say IB minus, as a function of IB plus minus the offset. Because if IB minus is the if the difference is I offset, then of course IB minus is IB plus minus I offset or plus I offset. Again, I offset is something that is with a polarity which is unknown, because this is an error between two signals which are supposed to be the same. Okay, now we know that if I have an error here, so let me just correct it. This is IB minus. Okay, we know that if the input currents are the same, or for the case that the input currents are the same, and with the right selection of Rx, V out will be 0. So we can actually cross out these two, which are actually canceling each other. We are then left with I offset by itself. And therefore, the error will be I offset over RF. Again, I'm eliminating the polarity here. So strictly speaking, this should be minus. What does it mean? It means that by introducing Rx, and even for the case of IB plus, which is different from IB minus by I offset, we are gaining. We are gaining because now, instead of having an error which is IB over RF, we have an error which is I offset over RF. Now, I offset is clearly much smaller, or smaller than IB, because it's a difference between two currents which are supposed to be the same. So we are gaining in any case, and therefore it's a good practice to put this Rx. Let me wrap up this presentation by a very simple exercise, and that is the following. Suppose we have a source, and this source has an internal resistance of 1 mega, large resistance, large DC resistance. Okay, and here's the amplifier. It's a non-classical. There is a connection to ground here, and the question is, what is the value of Rx, and where shall I put it? As I've said before, the easiest way to do it is to cut out this amplifier, to look at the impedance here, and see what's happening. When we look at the impedance here, we see 10K in parallel with 10K in series with 10K in parallel, because this is now ground. So this is the value, and as it turns out, this is about 6 kilo. When we look at from the input, the plus input terminal, we see this 1 mega. Now obviously they are not matched, so I have to add just about 1 megam to the R minus. We have to add to the R minus. So the next question is, where to add it? Well, if we add it here, that's bad. Although we'll comply with the requirement, because now we can get a much higher impedance, or if we put some resistance here. But the thing is that we are going to change the amplification with respect to the source. Here, the source. So we have to find a place in which the DC will be affected, the error of the current, of the input current, but the gain of the amplifier will not be affected. Now, the place to put this resistor will be here, because if you put a resistance in series with a input of an operational amplifier, this does not change first degree. This does not change the amplification or the gain of the amplifier. It is affecting, of course, the DC error due to the bias current. So by putting the Rx here, and the value of which will be just about 1 megohm, you can compensate this amplifier from the DC point of view and with very little change on the amplification, although there might be some changes due to capacitance of the input, but this is not the issue we are talking about here. This brings me to the end of this presentation. I hope you'll find it useful to you, and thank you very much for your attention.